Nā ku te roro, nā o te roro ka ora ai te iwi. With my basket and with your basket, the people will prosper. Ena mana, ena reo, e rā rangatira mā, tēnā koutou, tēnā koutou katoa. Kia ora, colleagues, guests, friends of the University of Otago, Vice-Chancellor, Deputy Vice-Chancellor, Pro-Vice-Chancellors, heads of department, and of course our distinguished speaker tonight, Professor Dave Craw from the Department of Geology. It's a real pleasure to be able to welcome you here tonight for the 2018 Distinguished Research Medal Lecture. My name is Richard Blakey. I'm the Deputy Vice-Chancellor for Research and Enterprise, and it's great to be here to share and celebrate the award of our most highly esteemed research distinction. That we will have the order of proceedings being an introduction of the speaker, the Distinguished Research Medal Lecture, and then we'll, after the presentation of the medal by the Vice-Chancellor, we'll have a small opportunity to share with you in some refreshments at the Staff Club. We have Professor Craw's Head of Department, James White, here to give a formal introduction for the lecture, outlining the details of his career and achievements that have led to this award. But as I chair the panel that advises the Vice-Chancellor on the award of the Distinguished Research Medal annually, I'll first give you a brief introduction as to the nature of the award and the kind of distinction that is needed in order to get this, our highest research accolade. Our regulations state that the University of Otago Distinguished Research Medal Award aims to give recognition to outstanding performance of individual researchers. A medal commemorating the award will be presented to each recipient at a public lecture given by the recipient tonight. And I'm sure Dave will be able to let you see the medal, which actually I should say we've had a new medal struck this year as part of our refresh that I would welcome some feedback on. The basis for selection will be outstanding scholarly achievement, including the discovery and dissemination of new knowledge, the development of innovative technology, or the development of concepts that lead to significant advances in activities in the university. These are very, very high standards to set, and we aren't required to make an award every year, but in this case, the panel felt that Dave's nomination certainly met all of those standards. Now, what happens is all of the academic departments and divisions are invited to bring forward nominations and submit portfolios from their best and brightest researchers. And we seek views of others to help guide our decisions. We get independent referees reports solicited by the nominators that then come in, and I have the most difficult task to chair a panel that includes previous Distinguished Research Medal winners to try and select from all of the breadth of disciplines that we have, which of the nominees best meets the award criteria. And what makes this special is, actually, Dave, tonight you join a very exclusive club. We very rarely award more than one Distinguished Research Medal. Sometimes it will go to 2 recipients. Where unlike, for example, the Nobel Prize, there may be in any one discipline 3 awards in any one year. So we have to select one recipient across all of our disciplines rather than making awards in individual disciplines. We have to balance overall career-long scholarly achievement with the discrete world-changing discoveries that are often sufficient for other awards. So just one discovery is not sufficient. It has to be a significant career-level achievement. So putting the scale of the exercise in context, we have at the University of Otago approximately 1,600 research-active staff who would be eligible for this award. And with only one Distinguished Research Medal awarded each year since 2004, there are only around a dozen and a half recipients of this award in the club that you are joining, Dave. So that represents about 1% of our academy. Consider also that to be appointed to be an academic or a researcher at the University of Otago is also highly selective. We can typically get more than 100 applications for any one position, so that's another 1% selection. So in that, you're 1% of a 1%. But even getting to the level of a PhD where you are suitably qualified even to apply for one of our positions, that's about another 1% exercise. So here we are tonight to celebrate the 1% of the 1% of the 1%. And Dave, you are officially tonight the smartest person in New Zealand's smartest city, and most beautiful city. I hope that you're able to dine out on that fact very well tonight, and at least for the next year, that you can claim that because I said it, it must be true. So as a final remark before we hand over to Professor White for the formal introduction, one thing that's special about your award tonight is it's linked to one of our founding professors that I want to make, Professor James Gow Black, who was also a geologist and a chemist, our inaugural Professor of Natural Sciences. And for James Black, the practical application of science was the central focus of his career. In his introductory lecture at the opening of the university's second session in May 1872, according to the Encyclopedia of New Zealand, Black claimed that one of the aims of a scientific education was to enable a person, quote, to produce a pound of corn or wool or iron or gold at half the expenditure which it previously cost. And I'm looking forward then tonight to your lecture on Otago Gold to see what resonances and parallels there might be with the views and the work of Professor Black coming close to 150 years ago. Anyway, ate ake nei, that's enough said from me. So with that, I will now invite Professor White to come forward and provide the formal introduction. Thank you very much.
Greetings, and thank you all for being here to listen to Dave. You're not here to listen to me, so I'm going to keep this fairly short. Dave's been with us for a long time. He first came to Otago as a Bachelor of Science student, and that was in 1972, if I'm counting right, so 46 years. He stayed for the BSc, then went to Canada for a while for his master's, came back for a PhD, went back to Canada for a postdoc. Then he came back here, and he's been here with us for over 35 years now in the Department of Geology, is one of our mainstays, significantly longer than I've been here. During that time, he's produced more than 300 publications, a tremendous number of those with students, and many others first authored. So this is an amazing achievement in earth science. And he's done that while finding time to keep up with his joy of being outdoors. So he's a man who's keen on the wilderness. So he's managed to do the writing in between, finding time to go to Patagonia, Antarctica, Baffin Island, South George Island, the Canadian Yukon, Nanga Parbat, and Tibet. Most of those more than once, not all of them. His PhD was on Mount Aspiring National Park. And this is the kind of PhD that we used to do in geology at Otago. It was the whole thing. So 2,000 square miles, 3 kilometers of relief, more than 7 accumulated months in the field for that PhD, all done within the PhD time period. So Dave's impressive. And the other thing that all of his nominators, all of his letter writers commented on is that he's changed the way that the world looks at how gold moves around in mountain belts, how it's extracted from the earth, moves with fluids, and ends up to be in the hard rocks where it's sourced. And then he's done the same thing again, looking at how that gold is then moved out of the mountains down into alluvial gold, where we can pick it up in the rivers. And rather than tell you more in my words, I'll give you a bit of an outline of what Dave's going to talk about. So he's going to tell us about gold and gold mining, from alluvial gold, which is the gold rush days that built Dunedin, through to modern mining, which is largely hard rock, places like Macraes. He's going to talk about graphitic carbon, so black carbon, metamorphic in gold in mountain belts, and how that tells us about how we can mobilize tiny amounts of gold and large amounts of water, bring them into the mountains and turn them into a resource. Then he's going to link those mountain sources with alluvial gold. And his most recent foray into that, working with other people, has been using fish DNA to do that. So that's not a standard approach to finding out how things move from the mountain into the basin. So that was has been a very productive line of research that's unique to Dave. And then he's going to tell us a little bit about mine waste, both as a hazard and as a resource. So the stuff that we used to process, we didn't get everything out. We can go back. He'll tell us more about that. And one of the things that makes that possible is biology. So he's going to also talk to us about bacteria and gold and bioleaching. I think I'll let Dave tell you now. Thank you.
Well, thanks very much, James. It was very flattering. And you could have given the talk for me, actually. You were doing very well. I have a whole lot of different directions that I go along with research. And I work with a whole lot of different people. So the talk tonight will involve moving around all over the place, I'm afraid. I'll have to jump around. But the first bit, I'll talk about history, because we've got a university that's got a 150th anniversary next year, and the gold has been very important for that. And then the end of the talk, I'll talk about the future, the present and the future. So that's the aim for the beginning and the end. And in the middle of the talk, I'll do a lot of the things that James just said. I'll talk about a whole lot of different directions, and they're sort of interconnected, but I'll have to hop around all over the place. So first question that people ask me all the time, because mining is a sort of a dirty word in society nowadays, and I'm quite happy to be a social outcast, and that's just the way it is. I enjoy that. And mining is a good place to be from that point of view. But why do we mine gold? It's because people want it. It's as simple as that, really. But people ask me this question all the time. It is an amazing metal. And it was the first metal we came across way back, 7,000 years ago, or thereabouts. It was the first metal we started to use instead of stones. And you can see on the right there, I mean, that's not a bad day's work for somebody nowadays. And 5,000 years ago, that's pretty impressive. Gold is really easy to deal with from that point of view. It's got a huge number of different uses, and you can see here it's getting more and more uses. Somewhere between 10 and 20% goes into the computers and cell phones. You've got these cell phones there, and you can see that the bit that Gemma's holding there is doing our little bit for the cell phones. 170,000 phones can be made out of that bar, or 50,000 laptops, and cars nowadays are computers on wheels. So that's why we mine gold. And going to Otago, the link with Otago, the top left picture there, Dunedin, 1860, 2,000 population, a real Mickey Mouse one-horse town. There's the horse, actually, for the one-horse town. And 1 year later, completely transformed into a gold rush city. And if you want to know what it was like, Eleanor Captain has done a really good job. She captured the atmosphere of a goldfields environment. It was set mostly on the west coast, but it could have been anywhere in Otago. Dunedin does get a look in that book, and it was a very unpleasant place. 9 years after that picture was taken, they set up a university, and it was the cash that came through that gold rush that set up this university. It didn't come to this site, it didn't have those buildings at the time, but very soon afterwards they started to build the university, and it's just been growing and growing ever since. I started my career torn between the School of Mines, which was originally opened in 1879, and the Geology Department, which grew out of the School of Mines in 1916, and I was torn between the two, walking backwards and forwards across that quadrangle. The School of Mines closed, and so I stayed in the geology department. So getting to the gold world, this is Otago Gold. Just put into some kind of context, this is the production that we've had in cubes. That's the amount that we've produced over the last 150 years or thereabouts, 160 years. The top cube there, 8 million ounces, came out of historic mining. This was the gold rush and all the mining that came afterwards. And almost all of it was the alluvial gold in the river gravels, more than 95% of it. Nowadays, since 1990, there's a gold mine, which I'll talk more about, the Macraes mine not far from here, and more than 95% of the gold that's coming out over the last 30 years or so has been from that environment. So there's the two different types of gold, and I'll be talking about both of those. All right, so where did it all start? Start with alluvial gold, with the gold rush. Everybody in this room should, at some stage, make a pilgrimage down to Gabriel's Gully, where the gold rush started. It's a dock reserve now, and so I'm not allowed to take students there in gold panning anymore, but it was a good place in the past for field trips. So that's where it all started. It was that particular sedimentary unit, the river gravels there, the largest production from a single deposit in Otago, and it's still the largest deposit in Otago. And the reason it's still there, it was called the blue spur cement by the miners. It's old, it's very old. It's the oldest gravel that we have still preserved in Otago, and it's been cemented by groundwater, so it's very, very hard to work. And as a result of that, there's quite large deposits of it still there. So it's 80 million years old, and that's from the time when we were still attached to Australia. So it's Australian gold, if you like. This is what the gold looks like. These are gold flakes that have been hammered in the river, hammered out flat. The one on the left is so thin that it's starting to get looking moth-eaten. It's got holes in it. And the one on the right has been hammered so much that it's folded and folded and folded and then flattened again. So that's what the gold looks like. It's about 1 millimetre or thereabouts, and it's scattered not very liberally through the rock. This is what it looks like when it's being made in the river, and it's what it looks like when it's been taken out. The processes are exactly the same. The gold extraction process haven't changed significantly since the Greeks and before the Greeks. Certainly the Romans took this to industrial scale 2,000 years ago around the Mediterranean and further north. So things haven't changed very much since. And this is exactly how a river works in the natural environment. So you have lots of water moving a whole lot of gravel, and the gold, because it's very dense, will accumulate. And you can see that at the end of the red arrow, it's just accumulating. There's the little flakes there along that riffle within the gold-saving system. One of the notable things there is the muddy water, and this is one of the things that has been in the news. It's been in the Otago Daily Times almost regularly since the Otago Daily Times started at the beginning of the gold rush. And that is that the farmers and the other people complained about the miners putting muddy water into the river. And there's a miner who has just, I think he's closing down now. He was tackling this material very bravely, and he couldn't keep control of all the muddy water. There's a picture of Gemma over her gumboots in the mud. It is just phenomenal. Now, the picture on the top left is during the gold rush. They didn't actually mine this hard rock during the gold rush. They mined the gold that was liberated naturally downstream of it. So that's looking down towards Lawrence from Gabriel's Gully. It's a very famous picture. After they'd totally stripped out that valley and all the time they were sending mud down onto their neighbours, and so it must have been an incredibly unpleasant place to be. But after they'd done all of that, they started working into that hard rock and it got even muddier. So it was a pretty unpleasant sort of environment. That muddy sediment contained some gold, and a lot of that has been reworked and reworked and reworked ever since. And that reworking is what I used to take students to go and do. We can't do anymore. All right, so we've got this large deposit of gold, Gabriel's Gully, down near the Clutha River there, down near Lawrence. And the question that was asked at the time, and has been asked constantly ever since, is where does all of this gold come from? And it's sort of embarrassing for me to sit here with the senior university management and admit that they've been paying me for 35 years and I still can't answer that question. And all I can do now is explain why. So we've got Gabriel's Gully down there, and with the gold, we find these distinctive minerals you can see up on the top right. The left one is a garnet, the right one is a magnetite. They're very distinctive minerals, only found in the central part of Otago, to the northeast and to the north of Gabriel's Gully. So we know the gold came from up there somewhere. Was it 10 kilometres or was it 100 kilometres? That we don't know. But a very common belief amongst the gold mining fraternity over the last 100 years, and especially over the last while, is that because Macrae's deposit, which I'm going to talk about now, it's the largest gold deposit in Otago within the basement rocks. It's the other kind of gold in Otago. It's the largest deposit, and therefore it's likely that the gold came from there across Otago to Gabriel's Gully. And you can see that the river system doesn't allow that to happen very easily now. So there's Macrae's, taken from above. It's a very large mine on a New Zealand scale. It's even on the radar internationally. It's a world-class mine. Something like 10 million ounce resource totally, although they may not get all of that out. They've produced 5 million ounces over the last while. I showed that with the cube before. And importantly, for trying to figure out where the gold came from for the Gabriel's Gully area, the Macrae's deposit is about 1,000 times bigger than any of the other ones that we know about. So it's a pretty good candidate. It's quite a spectacular structure. It's a geological structure, a 30-kilometre long gold-bearing fault zone that goes all the way from up near Hyde all the way to Palmerston. And this is just a small portion of it that I've got there. What does it look like? You look at the rock. The rock is schist, which used to be sedimentary rock, but it's been buried quite deeply, 10 to 15 kilometres or at least, and temperatures above 400 degrees. The processes I'm talking about happened about 140 million years ago, so that was a long time before Gabriel's Gully formed. We're talking deep time now. And you can see the white bands going up through there with the arrows. That's where the water, the hot water, moved through the rock. Those were fractures at the time. The water was moving through the rock and transporting some gold, arsenic, and iron, and other elements. The yellow bits that you can see there, that's fool's gold, so that fooled you, didn't it? That's not gold. Those are sulfide minerals, pyrite and arsenopyrite, and they pervade the rock. They were brought in during that hot water process, 10 kilometres down, so it's way down. All right, and that's what the gold looks like. This is now looking at microscopically. This is looking inside one of those pieces of fool's gold, and you can see that I've ringed a whole lot of them. Those are the real thing. There's a whole heap of them there, and they're about a micron, a few microns across. They are tiny. So they're distributed right through those sulfides, and those sulfides are distributed through the rock. Very, very hard to get this out, and I'll talk about getting it out later. But the first thing that you're going to tell me is, well, that's only a micron across, and the stuff in Gabriel's Gully is a millimetre across. Obviously, the gold at Gabriel's Gully didn't come from Macrae's. But it's not that simple. There's a zone just below the surface, all over eastern and central Otago, where the rock has been altered by groundwater. It's clay altered and oxidised, so all of that brown is basically rust, it's oxidised iron, and within that, the gold has moved around in solution. This is low temperature mobility of gold in the top 20 to 50 metres. And this zone has been very important historically for the miners. The small amount of hard rock or schist-derived gold that was extracted historically was from tunnels like this. People digging along the gold-bearing zones and pulling out gold. They couldn't save that tiny gold. Whenever they got through this brown stuff, they got into the tiny gold and they stopped. And this is a worldwide problem that was around certainly right through the 1800s and into the 1900s. Getting the tiny gold out of these deposits was essentially impossible. So this is the gold that they were finding as a result of the groundwater movement, the oxidation process, the clay alteration, all of the chemical processes that were going on was also moving gold around. And instead of having those tiny bits, we had accumulation of a smaller number of larger bits of gold. And that's what they look like. And lo and behold, they're about a millimetre across. Actually, some of them get quite big. Those are quite nice. But we don't see very many of those, and obviously they're not going to travel very far. Some of those are this big. They're quite spectacular. So those are nuggets. Otago, by and large, is not a nuggety sort of place. Mostly the gold is very fine, but every now and again we come across these rather nice ones. The top left one and the top right one, I'll ask the Vice-Chancellor to block her ears now, I bought with beer. Well, getting back to university history, you can see that on the map there up near Macrae's. Now, there was another area where there is a small amount of this similar sort of gold, and it was on the Bearwood Run. The Bearwood Run was given to the university as an endowment when it was set up, and it was for farming, and the university rented it out to some poor cocky who was farming a very small number of sheep and a very large number of rabbits. And I don't think they made very much money of that at all. But there was one of these gold deposits discovered on it. And there was a lot of excitement. And even when I first started my job, there was the odd cheque coming across my desk from the Bearwood Mining Company. They were still having to pay royalties. Now, they weren't producing much in the way of gold. They weren't actually producing any gold, but they had to pay to have the rights continue. The university sold the land a while back, and so those cheques stopped coming. I think they probably made quite a lot of money out of the land, and that was very sensible. So what was the story there? You can see in the bottom left, there's you probably can't see it, but there is a grain of gold there that is about 0.5 millimetre or thereabouts, and that's the sort of gold that was found in the brown oxidised zone. That's a cross-section there showing where they had their shafts going down, and just like at Macrae's, they got down to the bottom of that brown stuff, and that was it. And so no more real royalty checks came to the university. It was all over. So that was probably University of Otago's only mining venture, and it was a total disaster. All right, so we're moving on now. We've still got this problem that we've made some gold that's big enough to get from Macraes to Gabriel's Gully, but the river system nowadays is not right. How do you figure out how rivers move, how they change? There's our two main rivers in Otago, the Clutha and the Tairi. The Clutha is a very long river that goes all the way from the main divide to on the west to the sea in the east, and the Tairi has this convoluted eastern Otago course that starts. You can stand actually at the airport, look out the window, and you can see the head of the Tairi River that's going to go for 250 kilometres and end up just outside the other window. They're both the same length. Crazy. And from the gold point of view, one of the notable things about the Tairi River, even though it flows right past the largest bedrock gold deposit in Otago, the currently active mine at Macraes is overlooking the Tairi River. The Tairi River has almost no gold. Most of the gold in alluvial gold in Otago is in the Clutha system. So it's an interesting conundrum. How can we sort that out? Well, this is now looking south. We're flying above the Maniatoto. We're looking south into the upper Tairi River and over into the Clutha River. You can see Macraes down on the bottom left and Gabriel's in the centre at the top. And this is how we figure out, well, this is one of the ways that we figure out how rivers have changed over time. One of the good things about Otago is that we have a zoology department. And within the zoology department, we have geneticists, John Waters and Graham Wallace. And what they have shown is that there's a fish there. There's two species. There's one in the Clutha catchment, Galaxius teviot up there, and there's one in the Tairi catchment, Galaxius depressiceps, and they used to be in reproductive continuity. Not only can they tell us that, but they can give us an estimate of how long it was since they stopped being in reproductive continuity. And that's something like 500,000 years, give or take a bit. I mean, it's pretty rough. But what it means is that those hills in between Galaxius teviot and the Maniatoto plain there, those hills have come up over the last 500,000 years. And lo and behold, even I as a geologist can tell the difference between schist and greywacke, and we found very distinctive rocks that are only found up the north end of the Maniatoto. We found them over the other side of that hill with the fish. So there's no doubt that at one stage, the Tairi River, the upper Tairi River, which now flows to the north, it used to flow towards the south. And this is a reconstruction that, call it the Kyburn now. The Kyburn comes down and joins the Tairi River at Kokinga. And the ancestral Kyburn used to go all the way from the northeastern side of Otago all the way down to the Clutha River. And at that time, this is about 1 million years ago, it was taking all of the gold. And it deposited in that, quite a lot of it in that yellow circle, which I'll talk about in a moment. But that gold was stripped out of the headwaters of the Tairi and in the general vicinity of Macraes and taken down. Now you can see why I've been incompetent for the last 35 years is that this was a complicated story to unravel, and this is only 1 million years, maybe 2 at the most. How are we going to unravel the other 78 million years to try and figure out how the Gabriel's Gully things formed. We can't really do that. All we can do is make guesses that these sorts of processes were going on at the time. Now, the island block gold mine, just a lot of people have been past it. It's the top left there, and one of the notable things about it, the road to Alexandra drives right beside it. One of the notable things about it is that you can't see that it was a gold mine. One of my contemporaries, Noel Becker, is part of a small group of people in New Zealand who have developed a quite spectacular way of making environmentally benign but very productive alluvial gold mines within this sort of environment. And one of their challenges that they meet almost all the time is that the rehabilitated land should be more productive than it was originally. So what they do, they have a thing which is a sort of a floating processing plant. It's a more sophisticated version of one I showed before. The mine pit, looking up in the top right, the mine pit is advancing in the direction of the yellow arrow, and the tailings, the processed material is dumped out the back, and then it's bulldozed around and the sheep are planted. So this is a very effective way of keeping the muddy water on site and getting around that problem that I mentioned before was within the Otago Daily Times on a regular basis for well over 100 years. So it's a very good system. Noel Becker was responsible both for the island block one up there with all of the Taieri River gold that got swept down, but he's got the active one now in Southland. Just looking at that processing thing, it looks very much like a dredge. The historic dredges, they were developed in Dunedin, they were invented in Dunedin, and lots of them, dozens of them, were operating all over Otago a bit over 100 years ago, 120 years ago, and the concept was taken all around the world. Doug McKenzie and I have worked in the Yukon, and they've got a spectacular one there. It's a typical Otago dredge sitting up there for the tourists to go and see. It's one of the better preserved ones. So these things were taken from Dunedin, from the gold rush world, and taken all around the world. Okay, so we've got a pile of gold there on the bottom right, millimetre-sized gold flakes. I keep on talking about those. They're the easiest ones for the miners to extract. All very uniform grain size, and that's because the finer gold they can't keep. It just gets washed away, and it's very, very difficult for them to process that. So fortunately, we have a world full of bacteria, and the bacteria are on the side of the miners. So up in the top left there, there's some typical millimetre-sized flakes, very thin. But if you look very closely on the surface, you can see that the bacteria have been busy. Looking at the bottom left there, they're making these little wormy and blobby bits of gold that are on the surface. So what they're doing is part of the same sort of process that I was describing before for the oxidised zone within the mineralised rocks at Macrae's. The bacteria are moving the gold around, depositing gold to make a smaller number of larger particles. And every micron counts in this sort of situation. The bacteria need to be fed, as we all do, and on the right there you can see we've got woody material that is very commonly within these sediments, and when the bacteria are active, they leave behind these iron sulfide. They're called framboids, which is basically raspberry-like, except that unlike a nice juicy raspberry, these things are only a few microns across. But these are bacterially deposited iron sulfides, pyrite, fool's gold, that forms in association with a lot of these processes in the bottom of rivers and within the river gravels after they've been deposited. This is an experimental study that was done by a group that I work with, but I wasn't part of this study. This is totally a lab-based thing where they got some bacteria and they fed them some gold-bearing water just to see what would happen if you fed bacteria some gold-bearing water. Well, it lies very heavy on the stomach, is what it boils down to. They don't like it, and so they kick it out, and so this is the result. These are bacterial gold poos, and this is what they do. They just got to get rid of it out of their system. Some of them put it into their cell walls, and these ones put it right out. And the notable thing is that they make these triangular and hexagonal crystals. Gold actually makes cubic crystals, or variations on cubes. But the bacteria are great at making these very thin hexagonal crystals and also little blobs and things. So my role in talking to these people that I collaborate with, they said, well, this is what we do in the lab. Can you go out and find that in the real world? And of course we can. This is Central Otago. There's quite a spectacular piece of hexagonal gold adhering to the outside of one of the flakes within Central Otago, and a whole lot of other crystals and irregular blobs. So there we go, larger scale than the other ones, but that's quite big gold poos. So I want to take the bacterial story a little bit further, and I should confess now I actually know almost nothing about bacteria, but I'm learning, and I really enjoy learning, because the microbiologists have got a lot to tell us. So in the top left, that's just something I stole off the internet to show you what it looks like when bacteria are actively making one of these raspberries, one of these framboids. They're sitting there, they're doing their whatever they do all day, which is respirate and so forth. And the end result of their life processes is to deposit the iron sulfide, the pyrite. On the right there, the big yellow one, there's a framboid, and that one is 200 million years old. It's from the sediment that makes up the Otago schist, but it's the sediment that hasn't been cooked like the Otago schist. So this was formed on the sea floor at the time of deposition, around about 200 million years ago. These bacteria were active then. And you can see underneath that big yellow one, we've got a more diffuse one, and that's a piece of a plant. And the bacteria have been sitting inside the individual cells of that plant fragment and depositing pyrite. Well, it's not just pyrite, and quite a lot of work I've been doing with, in collaboration with some people in University of Western Australia, is to look at these things in detail. And we find that it's not just iron sulfide, it's a whole lot of other metals as well. And you can see on that bottom picture that the different colours are pulled out with a different technique. The details don't matter. But we've got pyrite, which is dominant. We've got sphalerite, which is zinc sulfide. We've got cobaltite, which is cobalt arsenic sulfide. And all of these things have a little bit of gold. And that's almost certainly gold that's put into these things as gold poos, exactly like we were seeing in the river gravels, in the modern places in Otago. It's exactly the same sorts of processes, and a lot of that gold, we don't know how much, but this is pure speculation, a lot of that gold probably came out of seawater. The seawater there, 13 millionths of a milligram per litre. Lots of people in the past have tried to extract gold from seawater because, you know, it's a very attractive concept, but they've never been able to do it in an economic way. But the bacteria can, and they've been doing it here. So here we've got localised gold enrichment within the original sediments that made up the Otago schist. The next stage is to take that sediment and bury it a long way down, heat it up to 600 or thereabouts degrees Celsius, maybe 20 or 15 or 10 kilometres down, a long way down. And these lines are analyses of rocks from different levels all the way down. Now, these are all exposed at the surface now, and you can see the arsenic shows it very well. The arsenic is at about 10 parts per million in the low temperature rocks, but by the time you get to high temperatures, it's lost almost all of its arsenic. The antimony, SB, does a very similar thing, and the gold does a very similar thing, though not quite spectacularly. So this is how we get the Macrae's type of deposit. We take those little framboids with a little bit of gold poo and some arsenic dispersed through them, and we bury them, heat them up, and start to move those metals around. And eventually they get channeled through fault structures like Macrae's, which I mentioned before. It's a 30-kilometre long major fault zone, and the gold and the arsenic get deposited along there. As part of all of that, we've got carbon. The carbon is carbon dioxide and methane are generated from the organic material that I showed a picture of before. So all of this is happening within, or has happened, within this very thick sedimentary pile that turned itself into schist. The carbon matters because you go to Macrae's and the place is just riddled with carbon. It's carbon in the form of graphite, which is the most common form of carbon. It's used for lubricants and things like that. And all of the fault zone is just riddled with this stuff. It's closely associated with the gold all through that fault zone. It's one of the characteristic features. The bottom right one there looks like coal. It's actually got more carbon than coal, pure graphite. So graphite has been a bit of an obsession with me. I wanted to figure out how that got there and its relationship to the sort of system that I've been talking about. So what do? You've got to go to some place in the world where there's lots of carbon. And this is the southern Himalaya. We've got something like 5 kilometres of relief there, and an awful lot of that is limestone or calcium carbonate bearing rock. So that's a very spectacular pile of carbon within the growing mountain belt. And as a result of that, all of that calcium carbonate bearing rock, the limestone, is being buried underneath the huge mountains that are growing. They get buried down to 10, 15 kilometres or thereabouts by the overthrusting as the plate tectonic movement brings the whole Himalaya together. That generates carbon dioxide, and the chemical reaction is up there. You just take calcium carbonate, a bit of quartz, and you get a calcium silicate and carbon dioxide. In the bottom left, there's hot springs with carbon dioxide bubbling out, lots of it. And it's reputed to be, right along the Himalaya, something like 10% of the natural carbon dioxide that's generated by geology. So let's go to the northern Himalaya, and it's a very different situation. We've still got carbon, but the carbon is organic debris within shaly rocks. And that carbon, it's basically an oil-forming environment, and so you bury that and you generate methane. And this particular picture, we've got the Muktanath temples here. there's a methane seep coming out of the ground that's been burning for 1,000 years or more, and it's a sacred site for both Hindus and Buddhists. Lots of people go there for a pilgrimage to see the spring. I've done it myself. So in this part of the Himalaya, the carbon is dominantly methane. You go in between and you find that you've got both those shales generating methane and you've got limestones generating carbon dioxide. And the two combine, and there's the chemical reaction at the bottom there, carbon dioxide and methane giving you graphite. Now that's stopping global warming just by a very tiny little amount, by a natural process where precipitating graphite, that black coaly looking stuff that's along that active fault zone, some of that rock is half graphite. It is very, very carbon rich. Well, that's been important for the structure of the Himalaya because that fault zone is a spectacular one that goes right behind the Annapurna Massif. And because all of that graphite has deposited along the fault, it's focused the fault movement on a very narrow zone because that graphite is lubricating it. And as a result, you get that 3 kilometre high fault scarp. The mountain would go up anyway, whether there was graphite or not. But what's happened is that the graphite along the fault zone has localised the movement and made that spectacular fault scarp. It's probably the largest, highest fault scarp on Earth. So that graphite is important from the structural point of view. So can we look at that here? It's not so easy in the Southern Alps because we don't have so much carbon. The Himalaya is a great place to look at that because it's full of carbon. But along the Alpine Fault Zone, we do have carbon dioxide coming out in spring, got a little bit of methane, and on the bottom right corner there, little bits of graphite. This is pretty small. This is not big chunky lumps like there is in the Himalaya, but the process is identical to what I've been describing within the Himalaya. So we have graphite in fault rocks active within the Southern Alps. And underneath the Southern Alps, we have the same sorts of processes going on, adding some gold and some arsenic. And so we've got this combination underneath the Southern Alps of graphitic rock with sulfide minerals and with gold forming today. These processes that I've been talking about for 140 million years ago to make nacres are going on today underneath the Southern Alps. And at the bottom of the slide there, you can see that the graphite weakening rocks and has facilitated the gold deposition. It's partly chemical and it's partly physical, but the nacre zone there, this is the reds and oranges are where the best gold are, and gold accumulations are. That's along a 30 kilometre long zone, as I said before, all the way from Hyde to Palmerston. And looking back 140 million years, that was probably a major structure that was causing mountains. It wouldn't have been like Annapurna. It wouldn't be as impressive as that. But nevertheless, that structure was important in the topographic history, early topographic history of Otago. So we're back to nacres. I always come back to nacres just because it's close. And I want to switch direction now and talk about the present and the future. Goldmine tailings. One of the notable things about gold mines all over the world is that you take about 1 gram out of a tonne of rock. And the other, or almost all of that tonne, goes out to tailings. And that's what those are. And that's more than a square kilometre, and it's 100 metres deep. That's an awful lot of rock. It's got about 5 kilograms of arsenic per tonne, and we've got to think of that as a resource. It's also an issue. We've got to find some way of looking after it. But that figure there in white, 5 to 10% of global energy consumption goes in crushing rocks. And that's for stuff for you. Every one of you consumes something like 20 tonnes worth of stuff. It's mined for you every year. That's a huge amount of energy. So these tailings, they're produced as a normal part of the mining process, and we've got to store them for a long time. In the old days, there was no problem. You just threw them in the river, and they were all gone. And that, in a way, was a lot simpler. But nowadays, we're not allowed to do that, so we have to store them there. Square kilometre, 100 metres deep, that's an awful lot of rock. It's about 100 million tonnes, just to give you an idea. Okay, so what are we going to do? I deal with Kathy Roofout, who is an ecologist, and she's been trying for 20 years to teach me ecology. And this particular project, we were out in the snow in this particular day, but trying to find what will grow on tailings. There's not enough soil up there to cover this square kilometre. And if you can't cover it, then the wind comes along and blows arsenic all over the place and the neighbours complain. So, trying to get things to grow. And what we found is that the tailings, raw rock, just ground up, has all the required ingredients to grow plants. Nitrogen, phosphorus, potassium, sulfur, all these other things. Everything's there. But, and one of the notable things that came out of that was how high the nitrogen is. The concept of nitrogen in rocks was sort of a new thing, but Macrae's ore, you'll see in the bottom right there, it's actually got quite high nitrogen. So a lot of environments like this, it's the shortage of nitrogen that's the problem. Here, it's the shortage of phosphorus. There's actually heaps of phosphorus in the rock, but there's not, it won't release fast enough from the fresh ore to allow plants to grow easily. So we ended up choosing this particular species. We tried a whole lot of species. It was sort of fun, really, going up and gardening and whatever. What we found was that the fresh rock doesn't work all that great. But if you put some of that weathered rock, the oxidised rock, the clay-altered rock that I keep on talking about, very important layer. You put that on, and the next thing you know, you've got grass growing. It's great, great stuff. And they've got heaps of that. So it happened very quickly after that. And on the bottom left, there's implementation of the process. Put a layer of that weathered stuff on, orange stuff, and they threw a bit of super on just in case. But it works. It works very well. Very pleased with that. Okay, why does it work? On the left, we've got unoxidised rock, and there's the phosphate minerals. The details don't matter. But on the right, that orange rock that you get at the surface, the clay-altered rock, you get completely different phosphate minerals. Phosphate minerals are really, really important. In New Zealand agriculture, what we do is bring shiploads of phosphorus-bearing material from West Africa at great political cost and distribute it around here, and then we send it to China as milk powder. I mean, that's the process. This is a little bit more indigenous in that it's not quite so phosphorus demanding. So we can cover these things with locally sourced phosphorus-bearing material, and the stuff dissolves relatively easily. Now, the top right picture there, the cerium, lanthanum, yttrium phosphates, you may not have come across these. These are called rare earth elements, and they matter, and This is something it was a rather nice picture I got from New Scientist. This is the periodic table according to smartphones. So those things you've got in your pocket now have got all these elements and more. And because there are billions of them around the world, we are having to extract an awful lot of these things. On the left-hand side in the middle, you can see the screen. There's those rare earth elements that we've got in those phosphate minerals up at Macraes. And we're just putting over the tailings and growing grass in them. But we need those rare earth elements. We need all of these other ones. So these are potentially available from Macraes tailings. We can't get them out yet, but that is a potential resource. And in the future, we're going to have to do that for a whole lot of reasons. The most likely material that will come out of the tailings is tungsten, because there's 100 times as much tungsten as gold. The price of tungsten is not high enough to make it easy to extract economically. You can see in the bottom left the price fluctuates about fivefold on a regular basis, but it's an important part and a growing part of modern technology. We need that stuff. There's an awful lot of the tungsten in the mineral scheelite up at Macraes. You can see it's glowing purple in the dark. Doug McKenzie's been doing quite a lot of work on this in particular. The reason it's glowing purple with ultraviolet light, which is what it's doing there, is that it has rare earth elements in it that help it to fluoresce like that. So if we could get the tungsten out, we could probably also make screens for your smartphones. All right, so I've been through all of this and I haven't told you how we get the gold out of, the tiny pieces out of the sulfides. And in the middle of that slide, there's a point that if you take the stuff and crush it up, some of the gold will come out if you throw it into a cyanide solution. And that cyanide solution approach has been around for a bit over 100 years. It was developed in the 1890s and it spread around the world. And one of the main protagonists and a guy who helped to develop it and spread the word internationally and within New Zealand was Professor James Park from the Otago School of Mines. So he was a great advocate of cyanide, and the process hasn't changed very much for the last 120 years. But to get the gold to dissolve in cyanide, you have to liberate it from inside these other minerals. And that is the battle. You can keep on trying to crush it finer and finer and finer. That takes an awful lot of energy, as I was pointing out before. So there's two pathways that are followed. One of them is the high temperature pathway on the left, and that's the one that they use at Macraes. They heat it up, they have high pressure oxygen, they make an acid solution, very low pH, and the gold is liberated from the sulfide minerals that way. The other way of doing it is the low temperature pathway. It's called bioleaching. It works best in the 30s Celsius, also an acid solution. And that uses that particular bacterium, which is very popular there, Acidothiobacillus spirooxidans, and that works very, very well. So I'll talk about bioleaching in a moment, but just to mention in passing that you can reprocess these tailings. Once at Macraes they installed the pressure oxidation system. There's only about 5, I think, in the world. It's a very high-tech system. They installed it in 1999 and they reprocessed their old tailings and made money out of that. That was a very effective way of doing it, getting more. But that was getting more gold. It wasn't getting any of these other elements. So the problem we have with coming up with ways of getting these elements out, look at the figures there, $100 million facility to set up that pressure oxidation plant. Top of the line, a lot of research, whatever, and all they got was an increase in 5% in the gold recovery. Now, 5% of 5 tonnes a year for 20 years works out at 5 tonnes of gold, so that's not a bad investment. But what they won't do in the commercial environment is follow up on strange ideas from pointy heads who work in universities. They want to see something that will actually work. So the final example I want to use is one that's got me fired up at the moment, just over the last couple of years, working with the microbiological people in Brisbane. This is a copper gold mine in Brazil. I haven't been over, but it's a copper gold mine that's within a national park in the Amazon rainforest. And I just wanted to wind people up by pointing out that there's something like 4 times as much copper in an electric car as there is in a standard car, and this is where your copper for your electric car comes from, a national park in the Amazon rainforest. I hope that makes you feel good. See you later, Jim. So they're producing ore to make your electric car, copper and a bit of gold to pay the bills, and they have an awful lot of waste rock and tailings. So the project is to try and get extra copper and gold out of the waste. And over on the bottom right, we've got a picture there of the problem. Rock has got lots of iron silicates. It's a bit like the black rock that makes up our clock tower. Not the white one, which is limestone, it's the black one. And distributed within those iron silicates, we just have little bits. You can see the arrow bits there, little bits of yellow stuff. That's copper sulfide, and there's gold inside that copper sulfide. So our problem is that we've got gold inside copper sulfide, inside iron silicates, and we want to get all of that out. How do we do it? Bugs. Do it with bugs. Another problem we have in this situation is that the pH of the environment there is neutral, very close to neutral. And the bugs that most people use, Acidothiobacillus, ferrooxidans, likes a pH of 3 or even lower. But the endemic ones, I'll just go back a step, that the bioleaching that's often done with that bacterium, you just make it in a test tube. You grow it in a test tube and stick it into a big bucket about the size of this room actually, and let them work away. But here, the concept is to use an endemic strain of the same bacterium that has evolved to eat silicate rocks at a pH of 7. So you have to go out in the field and you get the bugs there. They've evolved to be quite different. They're not a different species, but they have a different ecology from their cousins that get made in a lab. And so there we can see on the right, Acidothiobacillus eating rocks and liberating the copper sulfide and the gold, the tiny bits that are encapsulated. You can see on the left there, we've got an iron silicate, tiny little bit of pink copper sulfide and gold up in the corner. And the bugs are eating that, eating the rock and letting that stuff out. So on the left there, you can see how successful it is. Just over a few weeks in the lab, this is purely lab work so far, you can more than double the extraction of copper from these silicate rocks. So this is just an example. It happens to be an example I'm fired up about at the moment, but we're going to have to do a lot more about this sort of thing. We need to become much more efficient with resource extraction, because this transition that we're in towards a low-carbon future is actually creating more demand for resources. The amount of resources that we're using is going up. And a lot of those resources are being generated with fossil fuels. In Otago, we're lucky. We can produce gold with electricity and a bit of diesel. But a lot of these other places around the world, we're meeting your demand with fossil fuels in this transition to a low-carbon economy. So there's major research topics for the future. We're going to have to get into this. I think it's great. And down at the bottom, the take-home message is something that I've learned over the last 35 years, is that on this campus, there's some really smart people outside geology department. Isn't that amazing? All right, so that's just a thank you. And that's the end.
Thank you, Dave. I have the unenviable task of giving a vote of thanks, and I will not go through the many threads and traces of what you said, but I will just highlight your point that multidisciplinary research is essential. And I think in what we've seen tonight with your tour de force, we can see that the world of the polymath is still alive and well, that in your own research, Dave, like Professor Black, you're not a geologist, but you're a geologist and a chemist. And more than him, you're a geologist and a chemist and a zoologist and a botanist and a social scientist. You gave us a picture and a story of those early days in Otago. You took us from Macrae's around the world and back again, and I think we can all reflect on that. Actually, I do have one little social story to tell about Gabriel's Gully. My grandfather and his brother would go in their vacations from their southland farm, and they would extract gold from Gabriel's Gully. They extracted in their youth enough for one wedding band, and the first to get married would get the gold for the wedding band, and that was my grandmother's wedding band out of Gabriel's Gully. So I think we can all link to a story from this, and with that I would like you all to join me to thank Dave for an excellent lecture. Now, my pleasure, before we retire for refreshments at the Staff Club, to invite the Vice-Chancellor to come and present you with the medal and a certificate.
Thank you. Thank you very much.
That ends the formalities. Please come and join us at the Staff Club. Thank you very much.